Right, so hello everyone. Welcome to this webinar series from our special interest group in IEEE Communication Societies on analog computing for signal processing and for communications. This is a relatively new special interest group, I think established about maybe 6 months ago. With our first series of webinars. We had the first webinar in January that was given by myself. And now today we have the pleasure to host Philipp del Hougne from University of Rennes to give this second webinar. So Philipp is an associate professor, CNRS associate professor in France, affiliated with the University of Rennes. He's also a visiting professor, Nokia visiting professors at Aalto universities in Finland. He graduated from Imperial College London in the physics department, and he received then the PhD degree in physics from University of Sorbonne in Paris. He held multiple postdoc positions at various places, and he's very active working on physics of wave propagation and the interactions with communication system design. So it's a great pleasure to have Philipp today. And before I hand it over to you, Philipp, let me summarize the rules of those seminar series. The talk will last for about 50 minutes. The audience will be muted. You're going to have the chance to type any questions that you may have in the chat. And at the end of the talk, we'll actually have a Q&A sessions for maybe 10 minutes, where some of those questions will be discussed. And if you have additional questions, feel free to unmute yourself and ask your questions directly to the speaker. So thank you very much. Thank you, Philipp, again for your time and for giving us this talk today. So please, the floor is yours.
All right, so I'll try to share my screen. Can you see my screen? I hope you can.
Yes, we can see it.
Okay, great. So many thanks, Bruno and Matteo, for the invitation and for organizing this webinar series. It's a great pleasure to present in this webinar series, and I'm very happy also to actually serve as an officer on the Analog Computing Special Interest Group led by Bruno. So this talk is titled quite broadly, Programmable Wave Domain Computing for Wireless Communications. I'll start off with a few general comments on motivation, definition, and some historical origins, and then I'll focus on three particular aspects that are closely related to my research activity. The first one, and this will actually be the main section of this presentation, is centered on prototype-aware optimization of real-life hardware for programmable wave domain computing. So what we're trying to do here is to bridge the gap between theoretical studies that often make quite idealized assumptions and real-life experimental prototypes that are subject to all sorts of constraints. So I'll talk about some subtleties in model formulation, proxy model parameter estimation, and also some model-based fundamental bounds. Then I'll say a few words about maximizing wave domain flexibility, which is a natural goal to pursue if we're talking about programmable wave domain computing. And finally, I'll talk about some efforts towards nonlinear programmable wave domain computing. And I'll finish with a roadmap for some future research directions. And actually, a lot of what I'll discuss is also covered in a recent perspective paper that is available as a preprint for those who are interested. So starting with the general motivation and definition, from the perspective of wireless communications, there's currently a heavy reliance on digital signal processing and a requirement for a lot of radio frequency chains. Programmable wave domain computing broadly refers to information processing that occurs at least partially based on programmable interactions of physical waves, in our case, mostly microwaves, with systems such as metamaterials or radio environments. And programmable wave domain computing essentially allows us to offload processing burden from electronic processors to the wave domain, where the signals are directly processed as they interact with the matter. And so that is enticing for a number of potential benefits that can relate to cost, energy consumption, latency, footprint, and so on. But one has to be very careful and actually in every specific scenario evaluate end-to-end whether these potential advantages actually apply. So there are many historical origins of ideas that led to where we are now in terms of programmable wave domain computing. I won't have time to discuss all of these research threads in this presentation, so I'll focus on a few that I have participated in. The first one that I want to mention is some efforts based on reconfigurable intelligent surfaces to perform different types of mathematical operations. The first one that we looked at was this experiment back in 2018, where we aimed for programmable matrix vector multiplication. We then looked at high-fidelity reprogrammable signal differentiation in 2021. And more recently, we actually built a wave-based physical neural network with some types of nonlinearity that I'll say more about towards the end of this presentation, also based on a wave system that is parameterized by a reconfigurable intelligent surface. Another origin of wave domain computing relates to an area that is known as computational meta-imaging. So here, the fundamental problem is that you want to image a scene, but the scene has many more pixels than you would like to have detectors. And so basically what is sought is some wave domain implementation of a high dimensional to low dimensional mapping that is sufficiently diverse for compressed sensing to apply. And so there was this seminal work in 2013 where they used the frequency diversity of a metamaterial aperture to realize in the wave domain that high dimensional to low dimensional mapping. The idea was then transposed to configurational diversity, where a dynamic metasurface antenna was used to provide that diversity, so different realizations of the mapping at the same frequency. And a little bit later, we also looked at an end-to-end optimization of that mapping. So instead of using a series of random configurations, we optimized the configurations end-to-end for a specific task, which basically means that the measurement process becomes task-aware. And so as you measure the information from the scene, you're already pre-selecting salient information. So it's some kind of joint over-the-air sensing and computing. And this concept of dynamic metasurface antenna is not only relevant to this computational meta-imaging topic, but it's also actually very much related to hybrid MIMO, where the fundamental problem is essentially the same. In traditional MIMO and massive MIMO systems, you have one RF chain associated with each antenna. And so when you have many antennas, that means you have many, many RF chains. And so the goal would be, again, to reduce that so that you could map from a low dimensional number of let's say, digital signals to a large dimensional number of antennas. Traditionally, the first proposals in hybrid MIMO, I think they date back to 2005, where the idea is to use some combining board. But of course, the very dynamic metasurface antenna that I already mentioned can also be used here, because you feed it with a few ports, and then the signal will scatter to the different meta atoms. And so essentially, this ultra-thin metasurface does the job of the combining board and the antenna array all in one ultra-thin structure. Now, with the advent of reconfigurable intelligent surfaces and stacked metasurfaces, there are also other ways of implementing this. For example, you can directly radiate the low-dimensional signal and then have it interact over the air with an RAS or a stack of RASs and so on. So on a very high conceptual level, all these embodiments are kind of very similar because they implement a programmable low to high dimensional mapping. Now, in any specific application, which one is preferable would depend on specifics of the application. One consideration might relate to compactness. And so in that sense, the dynamic metasurface antenna is probably by far the most compact architecture. One other important benefit of such hybrid schemes that I would like to highlight is that they imply no additional conversion between wave domain and digital domain. That is important because if you imagine you have a long processing pipeline that happens mostly in the digital domain, and then for one specific mathematical operation, you go to the wave domain, that means that you have to convert from digital to wave domain and then from wave domain to digital domain. And so there are these two conversions that might ultimately turn out to be a bottleneck in terms of latency, energy consumption, and so on. But in these hybrid MIMO schemes, actually, there is no additional conversion, and so you don't have these concerns that you're introducing additional conversions. All right, so that was it for general comments. Now I'll start focusing on the core of what I want to discuss today, which is prototype-aware optimization of real-life hardware for programmable wave domain computing. So the fundamental motivation here is that there are many theoretical works that study the optimization of quite different types of programmable wave domain hardware. I've mentioned a few. There are many others. But one question that I think about a lot is whether these algorithms can be directly applied to real-life prototypes. And so to think about prototype-aware optimization, the highest level conceptual question, I think, is whether the system is ultimately optimized by a central operator or not. It's very rare that it would be optimized in a decentralized manner. In fact, I'm only aware of one very specific optic setup where that is possible. So for the vast majority of programmable wave domain computing prototypes and concepts, the optimization is performed in a centralized manner. And then the next question is, well, is that optimization based on a model or not? There are actually quite a few recent works on model-agnostic optimization in the area of training physical neural networks. There are a lot of interesting ideas like in situ backpropagation, forward training, and so on. But that's for another talk. I won't have time to discuss any of that. What I'll focus on is model-based optimization. And so if the optimization is based on a model, then the fundamental question is whether, in terms of applying it to a real prototype, the fundamental question is to what extent the model matches the reality. In fact, in most cases, unless you put in a lot of effort, you would expect some model-reality mismatch, which can originate from the model architecture on the one hand. So for example, it could be that you're ignoring mutual coupling, or you're ignoring structural scattering, or you're ignoring quantized tunability, or loss, or whatever it may be. And on the other hand, the model parameters. So maybe fabrication inaccuracies are not accounted for, maybe component tolerances pose problems. And so if we want to perform prototype-aware model-based optimization on a real-life prototype, on the one hand, we need a physics-consistent model, and there are all these details that I mentioned already, mutual coupling and so on, that sound like a burden, but we'll actually see later in this talk that we can leverage some of these physical properties as resources, for example, to unlock nonlinearity. And on the other hand, we need to make sure that our parameters actually match the experiment. And as I'll argue in a few slides, in most cases, that means we should estimate the parameters experimentally. So I'll start by describing the physics-consistent real-life system model. The general approach is to partition the system into three entities. Antennas that we use to inject and receive waves, tunable elements, such as pin diodes or varactor diodes that we use to tune, and then all the rest, which are static scattering objects. And that lumps together metallic and dielectrics, scattering structures, point-like, distributed, structural scattering, environmental scattering, all of that. And then we proceed by describing the tunable lumped elements as virtual ports to that static scattering object that are terminated by tunable loads. That's quite abstract so far. I'll make it more concrete in a moment, but this level of abstractness is really the power of this point of view, because essentially it applies to any reconfigurable wave system whose tunability is based on tunable lumped elements. And so that includes systems that involve RISs, DMAs, beyond diagonal RISs, beyond diagonal DMAs, and all the other more recent versions. And I'll actually mention later in this talk, to make this concrete, how this specific model can also be applied to beyond diagonal RISs. But for now, I'll focus on this example to make things concrete. So we have a rich scattering environment. We have 4 transmitting antennas, 4 receiving antennas, and a RIS with many elements, which are actually 1-bit programmable using a pin diode. And so the system model that I mentioned materializes as shown here. We have this box, which is basically the static scattering system that lumps together all the static components. It has ports associated with the transmitting and receiving antennas, and a number of ports associated with the RIS elements that are terminated by tunable lumped elements. And so the big scattering system is characterized by some scattering matrix, and then we have another scattering matrix that characterizes the load network, and the connection of these two gives us the scattering matrix that we can ultimately measure. Now, in practice, the wireless practitioner actually doesn't get to choose the reflection coefficients of the loads directly. What happens in practice is that the wireless practitioner chooses some control signal that will be mapped to some physical scattering properties of the loads. So for example, in some experiment, you might select the 0 or 1 volt logical signals that control the bias voltage of the pin diode, and then that'll correspond to some reflection coefficients. But what you really pick is the control signal. Now, to formalize this a little bit, what we can then say is that the scattering matrix of the load network is diagonal, and it contains the reflection coefficients of the loads, which are essentially an application of this encoding function to the control signal. And then standard multi-port network theory tells us what the scattering matrix that we can measure at the antenna ports is in terms of the scattering matrix here in gray of all the static components and the tunable load network. And what you see immediately is that we have matrix inversions here. So in general, it's not a linear affine mapping from the configuration to the scattering matrix. And by rewriting this inversion as an infinite sum of matrix powers, we can actually get some physical insight, because that infinite sum of matrix powers actually corresponds to multi-bounds paths that encounter the RIS k times. And if we're interested only in the channel matrix, that's just an off-diagonal block of the scattering matrix, and so it has a very similar mathematical structure. All right, so and so I've described all of this so far for one example of a rich scattering RIS parameterized environment, and just to show you how general this approach is, I'll have just one slide here on a very different system. This is a dynamic metasurface antenna where you have feeds and meta atoms coupled to each other through some two-dimensional chaotic cavity. And I won't go into all the details here. All I want to highlight is that we're using exactly the same model. So here you can see the multi-port network structure in the equation. Here you can see the encoding function, which for binary programmability is actually always an affine mapping. So my point here is just to emphasize how general this approach is. It's not only applicable to RIS, it applies to dynamic metasurface antennas and many other systems. All right, so to use this system model, we need a set of model parameters that accurately describe our prototype. So how can we determine the model parameters for a real-life prototype? The starting question is whether we perfectly know all system details. If we assume the answer is yes, then we can ask whether we can evaluate the model parameters in closed form. And if that is possible, then of course we should do so. And then we can determine the parameters analytically. That's what is actually done in many theoretical works, for example, on RAS. If we cannot evaluate the parameters in closed form, but we have enough computational power, then we can also then we can extract the model parameters numerically with a single full wave simulation. Just to give you a flavor of how that works, here's one example where we considered a risk parameterized wireless network on chip. I won't go into the details of why we're interested in this, but basically it's a very complicated radio environment with a lot of continuous metallic surfaces, dielectric layers, structural scattering. And so basically in the simulation, you replace the lumped elements by lumped ports, and then you get this big scattering matrix that characterizes all the static components. And then using the multiport network theory, you can predict any possible configuration, and we verified that that is reasonably accurate. But okay, in practice, actually, it's quite unlikely for a given experimental system that you would perfectly know the geometry and all the material details. So we would have to ask the question whether we can directly measure the model parameters in experiments. So if that is possible, then that would be great, right? We could measure the parameters directly in an experiment. Unfortunately, usually that's not possible for two reasons. The first one is that the tunable elements are not connectorized. So you cannot unscrew the element and connect it to a measurement instrument. And the second problem is that the number of tunable elements is typically on the order of hundreds, which is not matched to the number of ports that a typical measurement instrument such as a vector network analyzer has. So typical vector network analyzer has maybe 2 or 4, maybe 8 ports, and measuring a 100-port system with that is quite difficult. So actually, in most cases, what we have to do is to measure the parameters of the model indirectly in experiments. That's what is the practically relevant scenario in most cases. So I'll discuss how we can do that now. And the general picture is the following. So the wireless practitioner picks some control vector V, and that maps to some physically observable end-to-end channel matrix H. And our model for how that mapping occurs is that, of course, we have first an encoding. Here it's for binary programmability. An encoding of the control vector in the load vector, and then multiport network theory that maps the load vector to the end-to-end channel. So the system parameters that we need to estimate are both for the encoding function, the possible reflection coefficients of the loads, and then for the multiport network equation, we need basically the properties of this big scattering system. Now, unfortunately, purely based on experimental measurements, the model parameters are usually not uniquely identifiable. We've looked at this in many recent studies, and even though we cannot uniquely identify the parameters, we can estimate a set of proxy parameters that accurately map any control vector V to any corresponding end-to-end channel matrix H. And so from an operational point of view, since H is essentially the only quantity that you can physically observe, you cannot tell the difference between these different sets of proxy parameters. And so they're all equally good in terms of, say, optimizing the risk configuration for some channel gain maximization or similar. You might wonder whether you cannot eliminate all the parameter ambiguities, but turns out that the conditions that you need in order to sufficiently constrain the problem are essentially never satisfied in typical hardware considered for programmable wave domain computing. There is a special case that we explored in the context of virtual vector network analyzer where we deliberately satisfy all these conditions, but that's outside the scope of this talk. Now, to give you some more insights into these ambiguities, I'll briefly describe them. So the first ambiguity is a diagonal similarity. So if you transform some of the some of the scattering properties of the static components, as shown here with the diagonal matrix D, then the mapping from the control vector to the end-to-end channel remains unchanged. Similarly, there's this complex scaling when you transform the loads and certain parameters of the static components, as shown here, then the end-to-end the mapping from V to H is unchanged. And then there's also this ambiguity, which is maybe the most intriguing one. It's a Möbius ambiguity where basically you have this mapping, is known as a Möbius function, where you map the reflection coefficient to a different one and you alter all the other parameters in some specific manner. And again, what you'll find is that the mapping from control vector to end-to-end channel remains the same. To illustrate that a little more, let's consider an experiment where we can actually observe that. So this is a small scale risk parameterized radio environment. So we have 4 transmitters, 4 receivers. And here we have 8 antennas that are terminated by tunable phase shifters. So this is somehow a modular risk design where we have actually connectorized the tunable loads, and each load has 64 possible states. They're shown here. And then we run one of our routines for estimating all the model parameters. And in fact, we run it 5 times with different seeds. And here are our estimates for the possible reflection coefficients of the load. So what you can see is every time we run the routine, we get a different set of possible reflection coefficients. The only thing that they all go through the origin, which is imposed by our estimation technique. And you see that some structure is preserved. So you see the circular structure is essentially preserved, but they're in some way shifted and rotated and scaled compared to the ground truth. And as it turns out, each of those sets of parameters is actually a Möbius transformation of the ground truth. And also, each of these parameters, together with the corresponding scattering matrix, actually is able to very accurately predict the end-to-end channel matrix. So when we have enough measurements, we reach precisions of almost 50 dB. And understanding these ambiguities is also important, for example, when you think about a very large system such as this RIS, where you might want to estimate all the parameters in a segmented manner, because otherwise maybe there are too many. You cannot afford to estimate all of them at once. And so when you segment the parameter estimation problem, you have to be aware of these ambiguities, because otherwise you cannot stitch together parameters estimated completely independently for different segments. And so that's what we looked at in this work. Basically, we need some sort of overlap. And if we take enough care, then we can get this to work. And even for this large RIS in a real life setting, we managed to get precisions above 40 dB for the system model that I presented. And we do see that taking into account mutual coupling is important. So for example, here we looked at maximizing the sum rate, and we get certain value here, 10.75. If we ignore the mutual coupling, we only get half of that. And also, the mutual coupling unaware model is quite inaccurate in terms of predicting the KPI. So for example, it predicts 5.3, it predicts 12, but we actually only get 5.3, which is quite a big mismatch. All right, so what we've seen so far is how we formulate the model and how we estimate its parameters so that it essentially almost perfectly describes a given experimental system. And so once we have this calibrated model, of course, we can start to think about optimizing the configuration of the RIS or other tunable elements and some other architectures to achieve some desired objective. This is typically a discrete optimization problem because the tunable load states are quantized. In fact, in most experiments, certainly in ours, they're 1-bit programmable. For example, a pin diode has 2 possible states. And as probably many of you know, there are many techniques for discrete optimization, such as genetic algorithms, coordinate descent, and so on. And I won't discuss these in this presentation. The only thing I want to mention is that coordinate descent can actually be substantially accelerated with a Woodbury identity. And we found that in many cases, it actually yields quite a good trade-off in terms of complexity and performance. But the more intriguing question, at least to me, is not so much about the detail of the discrete optimization algorithm, but rather a more fundamental question, because you run this discrete optimization and you get some result, but you have essentially no idea whether there could be some other algorithm that performs substantially better, because essentially you do not know how close you're getting to the global optimum. And so here, it would be very helpful to know some fundamental bounds for what performance is achievable, because then if you can see that whatever optimization algorithm you use gets within, say, 98% of the bound, well, then you can conclude that there's essentially no other algorithm that can perform substantially better. Now, how can we calculate such fundamental bounds for a given prototype setup? I'll discuss this question here for the simplest example I think that can be considered, which is isochannel gain maximization. So you can see the model specialized to the single input, single output case on the top right corner. Basically, some matrices become scalars and vectors, but it's still the one-bit programmable RIS. And okay, so how can we bound the achievable isochannel gain in a given experimental system for which we have calibrated an accurate system model? Well, the first idea that might come to mind is to use some norm inequalities to derive a rather simple bound. It's given here. And this bound turns out to actually be quite sensitive to the model parameter ambiguities that I discussed earlier. And what that means is that is actually an opportunity because we can tighten that bound by optimizing over the model parameter ambiguities. And then we get an optimized norm inequality bound where, we have essentially here the parameters of these ambiguity transformations, and we optimize over them to minimize this norm inequality bound. We get a tighter norm inequality optimized bound. But still, this bound is actually so simple that maybe it's not the best bound, not the tightest bound. Now, another possible bound is what I refer to as idealized beyond diagonal risk bound, because we have to satisfy these conditions, but if the loads are lossless and the scattering matrix seen from the risk elements is contractive, then there's actually a closed form global solution for the case in which this phi matrix is not diagonal but can be any unitary matrix. And so, of course, the unitary diagonal case is a special case of just the unitary case. And so if we have a global solution for where we allow phi to be any unitary matrix, then that'll be a bound to our problem. And the way to proceed here is to define an auxiliary variable, and then the problem can be reframed as maximizing an affine functional over an ellipsoid for which a closed form solution exists via some alignment procedure. And this is actually a procedure that was proposed first in this work by our hosts. The only modification that we had to make was that we defined the wireless channel as a power wave ratio, whereas in that work it was defined as a ratio of voltages. But it's essentially the same concept. And of course, because it's a global solution, this bound is by construction insensitive to model parameter ambiguities. The main issue with this bound is that we can only apply it if our loads are actually lossless. And now the third bound, which is, I guess, our main contribution in this regard to the bounding, is to derive a bound based on a semi-definite relaxation. So we can introduce, again, actually the same auxiliary variable, and then we can formulate the isochannel gain maximization problem as a quadratically constrained quadratic program, which, using standard techniques of lifting and semi-definite relaxation, yields a semi-definite program that we can solve with standard convex solvers. And then, because any feasible point for the QCQP is also a feasible point for the SDP, basically the solution of the optimizer for the SDP yields a bound for our original problem. That's the bound that we obtain via semi-definite relaxation. All right, so let's see these bounds in action. And we can show that this semi-definite relaxation-based bound is also actually insensitive to the ambiguities. So let's consider first, again, this wireless network on chip, just because we ran a full wave simulation, so we actually know the model parameters without any ambiguities. And so here we're considering three cases. The first one is that the two possible loads are short circuit and open circuit. And so in this case, we can evaluate all three bounds. You see the norm inequality bound in blue, the idealized BD risk bound in red, and then the semi-definite relaxation-based bound in green. And so you see there's a clear hierarchy, and the semi-definite relaxation-based bound is actually very tight. So we ran a couple of discrete optimization schemes, such as genetic algorithm, coordinate descent, and so on, and they actually get very close to the bound, which means that the bound must be quite tight. We also considered other cases, for example, where the possible loads are matched load and open circuit. So in this case, we cannot apply the idealized BD risk bound, but the other two bounds yield a similar behavior. The SDR-based bound is still very tight. And finally here, we considered two possible loads that actually correspond to a commercial pin diet. And in this case, probably because there's a little more absorption, the SDR bound seems to be almost perfectly reachable by the very simple discrete optimization, so it must be very tight. All right, so this was just numeric. Now let's look at this in experiment. And this is, I think, really one of the important points here, is that for a given experimental system where we do not actually know the details of the geometry and the material composition, we can estimate the model parameters the way I described earlier, and then we can evaluate these bounds for that specific experimental setting. And so this is what you can see here, basically for a very rich scattering environment all the way to a free space radio environment. And we observe qualitatively the same trends. So the SDR-based bound is actually very tight. In the rich scattering for larger numbers of RIS elements, there's a little bit of a gap. But in all the other cases, actually, we're almost able to perfectly reach the bound, which means the bound must be very tight. And we didn't even make any particular effort here. We're just using standard discrete optimization to see how to probe the bound's tightness. All right, so well, that was only a bound on the size of channel gain maximization. Of course, when we think about programmable wave domain computing, we'll be interested in bounding performance for more complicated objectives, such as the fidelity with which we can approximate a desired MIMO transfer function. That's something we're still working on, and so we'll probably hopefully have some results on that soon. Now, that was actually the main section of my talk. I discussed a lot about this prototype awareness, which I believe is very important in order to materialize all these ideas in the experimental reality. Now I'll move on to discuss a few ideas for maximizing wave domain flexibility. Like I mentioned, it's very natural when we think about programmable wave domain computing to want to maximize the programmability. And so there have been, I'll discuss 4 distinct ideas that have been explored in the community. The first one is to stack multiple arrays of tunable elements. The motivation here is that wavefront transformations that can be realized with a single metasurface layer are often limited. And so that naturally leads to the idea of considering stacks of programmable metasurfaces, and people have built these in order to overcome this limitation. There are a few common confusions about the notion of depth in these multi-layer stacks, so I'll try to clarify those. First of all, in the absence of nonlinear components, the overall realized transformation is always linear, and it can always be represented by a single matrix. And that there are nonetheless benefits of stacking over a single layer, but those benefits would relate to things such as the achievable fidelity, the achievable tunability, or the achievable efficiency. And this approach of stacking multiple arrays also encounters a number of challenges. First of all, it's bulky. I already mentioned this, I think, for the stacked intelligent metasurfaces. So you actually look at quite a bulky volumetric device that is maybe difficult to imagine as part of a base station. You need more tunable components, so there's a cost and a control circuit complexity. And also there can be some concerns about transmission efficiency, because these transmit arrays actually usually have limited efficiency, and so if you cascade multiple of them, you might end up with a overall not so high transmission efficiency. The second idea that has been explored is tuning non-local interactions, and this was actually pioneered by our hosts. So the motivation here is that conventional programmable metasurfaces are limited to tuning the local meta-element properties, while the non-local interactions are fixed. And so that led to this idea here in a paper from a few years ago by Bruno and others to add tunable components in order to tune these non-local interactions. And that has proven to be quite efficient and a fruitful area of study. There are a few subtleties. Oh, and actually we also built a prototype recently where we have some switches, and so we can actually have these tunable interactions in an experiment. Some subtleties, though, that I want to mention is that in most architectures, actually including the one shown here, the tunable non-local interactions are implemented with tunable lumped elements. And so what that means is that the programmability is actually point-like and in that sense local. But the tunable components are of course not in a one-to-one correspondence with the meta-elements. And also another important aspect is that in real-life implementations, usually you have delays and losses in the connection between the tunable components that are important to account for if you move towards experiments. And so one way of thinking about this that I explored a while ago is actually related to what I said at the beginning of my talk. So remember at the beginning I said, as long as your tunability is based on tunable components, you can always partition the system into antenna ports, tunable lumped elements, and static components. And so that applies also if you're parameterizing a wireless channel with a BD-RIS. So basically you have the radio environment with all its static scattering, you have static components of the load circuit, and then tunable individual components. Now, the conventional way of looking at this is to look at the load circuit combined, and so then you're looking at a non-diagonal scattering matrix whose entries are tunable, but actually in a correlated way. Whereas if you initially connect all the static components, then you have a cascade of the radio environment and the static components of the load circuit that'll be described by some scattering matrix, and then that has certain ports that are terminated by a diagonal scattering matrix whose diagonal entries are individually tunable. So from the practical point of view, that's actually very interesting. First of all, because it's nice to have independent tunable parameters. And secondly, because if you have algorithms for conventional RIS that were fully physics consistent, then you can directly apply them to BD-RIS. And that's what we did here. So we estimated and optimized a BD-RIS parameterized channel using conventional RIS mutual coupling aware algorithms. And so you can see here the ambiguities and the end-to-end channel parameters. We're using exactly the same algorithm that I mentioned earlier, but the end-to-end channel is accurately predicted, and this can also be used for optimization such as SISO channel gain. All right, and well, one of the challenges with this approach, of course, is similar to the previous one. You need more tunable components, which has a certain cost and control circuit complexity associated with it. The third approach to maximizing wave domain flexibility is to strengthen the mutual coupling between tunable elements. Now, this is a little counterintuitive because conventionally, many people try to actually neglect or mitigate mutual coupling because they view it as a vexing nuisance. But the intuition here is the following, is that with strong mutual coupling, the wave bounces more often between the tunable components, and so it accumulates more sensitivity to their configuration. This is actually something we try to verify experimentally, here using a dynamic metasurface antenna. So we're looking at the channel from the feed of that dynamic metasurface antenna to a receiver. And now in experiments, it's actually quite difficult to change the mutual coupling strength, and we don't want to fabricate tens of different prototypes. But what we can do in experiments is to adjust the effective mutual coupling strength in post-processing via time gating. So we have a certain impulse response, and if we truncate that at some delay time, and then we go back to the frequency domain, then we've essentially suppressed all the paths that dwelt for too long in the system. And so in that way, we have effectively reduced the mutual coupling. And so if we use that method, then the truncation time actually becomes a proxy for the mutual coupling strength. And what we see here is that as we increase the truncation time and hence the effective mutual coupling strength, the normalized sensitivity of our channel to the configuration increases, and that correlates with an increase in our ability to maximize the channel gain. At the same time, the Hessian also gets stronger, and so the mapping from configuration to end-to-end channel becomes more nonlinear, which is something that makes sense. As you might remember at the beginning of my talk, I emphasized this matrix inversion. So this is a fundamentally nonlinear mapping, and the stronger the mutual coupling is, the more nonlinear it is. So the worse is a linear or affine approximation. Now, also this technique, of course, has certain challenges. The first one is that the nonlinearity in the mapping from configuration to end-to-end transfer function is often viewed as inconvenient in terms of estimating parameters and optimization protocols. And of course, if we're more sensitive to the parameter configuration, we're also more vulnerable to any sort of conceivable perturbation. And finally, one strategy that has been explored is time modulation of tunable elements, which is motivated as follows. So traditionally, quasi-static programmable metasurfaces are reconfigurable, but they're static during a given measurement. Actually, all the experiments I've shown you are quasi-static programmable metasurfaces in the sense that we can reconfigure them, but we keep the configuration fixed in a given measurement. Of course, if you start to modulate the configuration during a given measurement, then you unlock new degrees of freedom, and that's what space-time coding programmable metasurfaces try to leverage. This, of course, also is associated with its own challenges, notably high control circuit complexity to synthesize these rapidly time-varying control signals, and there's, of course, also a risk of sideband pollution. All right, so in the remaining 5 minutes or so, I'll say a few words about how we can move towards nonlinear programmable wave domain computing. The motivation here fundamentally is that almost all advanced signal processing techniques require nonlinear operations. For example, if you think about the universal approximation theorem for artificial neural networks, that hinges on the nonlinear activation functions. But for the typical programmable wave domain computing hardware, like all the ones that I discussed based on RISCs, DMAs, and so on, usually you're implementing a reconfigurable linear operation. So you encode your input data into the input signal, it scatters through this tunable linear wave system, and then you detect the output signal. So that's a linear mapping from input to output that you can control by choosing the configuration of the tunable parameters. But how can we move towards nonlinear programmable wave domain computing? So the key question here is actually, first of all, how we encode the input data. So I just assumed that we encode the input data into the input wavefront X. If we do that, then we can, of course, try to have some wave domain nonlinearity, although that is usually difficult because it tends to require very high signal power levels. We can also have analog electronics nonlinearity. In both cases, we would be looking at something like this, where we have a tunable linear wave system, and then we have some nonlinear circuit component. Or, of course, we can try to have digital domain nonlinearity, where we would basically detect the output signal. Detection itself is oftentimes already a nonlinear process, and then we can perform nonlinear operations on it in the digital domain. However, there's also a whole other strategy of encoding input into structural parameters, so the control vector of our programmable wave domain hardware. And in that case, we get encoding nonlinearity and structural nonlinearity. So these are directly related to what I discussed about the system model. We have an encoding function that maps control vector to load vector that is generally nonlinear, and then the multiport network function that maps load vector to end-to-end channel is usually also nonlinear because of mutual coupling. So that's encoding nonlinearity and structural nonlinearity. And so, schematically, this looks like this. Basically, the input data is encoded into the tunable parameters rather than the input signal. to show you a few experiments where some of these ideas have been explored. Here's one implementation of nonlinear analog electronics. There's quite a few implementations of digital nonlinearity. So you have some detection, then you do nonlinear operations in the digital domain, including the end-to-end optimization for sensing that I mentioned earlier. And here, of course, the structural nonlinearity is what we exploited in our physical neural network based on a RISC parameterized chaotic cavity. So here we encoded the input information into the RISC configuration, and then the mapping from RISC configuration to the measured transfer function was naturally nonlinear. I'll just briefly mention here some of our ongoing work where we try to sort of understand the contributions of these different effects to the expressivity of a nonlinear programmable wave domain system. Because I already mentioned the encoding nonlinearity, we have the structural nonlinearity, and if we cascade multiple layers, there's also the number of layers. And so these are three contributing factors to potentially increasing the expressivity in terms of, say, approximating a complicated nonlinear function. And so we're currently studying this by considering this chaotic cavity that is parameterized by an RAS. And we look at some physical neural network architecture where basically every layer relies on this architecture. And we encode into the loads both the input vector and then we have some trainable parameters. Well, these are preliminary results, but we see that we can partially compensate the absence of one of these effects through the other. So for example, when we eliminate encoding nonlinearity by imposing that the reflection coefficients of the loads are actually our input data, we can leverage stronger structural nonlinearity and more layers to compensate. And structural nonlinearity, we can control its strength through the time gating approach that I mentioned earlier. But yeah, if things are set up nicely, you can see that we managed to accurately approximate highly nonlinear functions using this linear wave system where we encode information into the input data. With that, I'll wrap up. I just have this one slide left of a roadmap where there's basically a lot of work left. On the device level, for example, there are some fundamental questions related to fundamental bounds and realizable functions. I hinted at that in my presentation. There's probably a lot of room left for finding principles to miniaturize devices, to add nonlinearity, memory, and so on. And I think it would also be very intriguing to discover principles for decentralized self-configuration. On the application level, I think we urgently need real-life demos of real-time optimization. We need to think about evaluating metrics such as power consumption and latency end-to-end. Map out the complexity performance Pareto frontier. And also we should assess the amortizability of, for example, adding nonlinearity in specific use cases, because it might turn out that the cost in terms of energy consumption or latency actually outweighs the benefit. And even on the network level, there are some challenges, such as thinking about physics-aware slicing of the hardware associated with the programmable wave domain, and all the way to security. And with that, I'll wrap up, and I'm happy to take questions.
Thank you very much, Philipp, for the great talk. We have one question in the chat from Faisal Athin. Philipp, can you see the question?
Yes. Yes. You want me to read it out? Or?
Yeah, so the question is about how would you practically implement high-resolution beamforming by only processing in the analog domain?
Yeah. Well, in principle, you can use a single feed DMA, and if you have enough tunability in the wave domain, you can control the radiated field purely based on how you configure, say, the pin diodes or the reactor diodes. Of course, if you add more feeds, then you have an additional degree of freedom, which lies in the excitation signal, and that can be helpful. But if there's some reason to limit yourself to single feed, then in principle, it seems possible, and you can explore all these options that I mentioned about maximizing wave domain flexibility to maximally control the transformation from the single feed to the radiated field. And there's a second part to this, I guess.
Yeah. Did you consider insertion losses in the analog computing?
Yes. So, I mean, in the scattering representation of the system, that's sort of naturally accounted for, right? Because the scattering parameters that map the inputs to the outputs, I mean, the information about the insertion loss is in them. And so as long as we're correctly predicting the end-to-end transfer matrix, uh, all such information, such as insertion loss, is naturally accounted for.
Okay. Any other questions, anyone? You can unmute yourself and ask your questions directly to Philip if you have some. I don't see any other questions. So maybe I have a question. I mean, on these nonlinear functions, computations, do you think there are some types of functions that are easier to implement in the analog domains than others? And what would be those type of functions?
Yes. So, I mean, I think, for example, matrix inversion, and I mean, there are quite a few works, including some from yourself, where because you have this matrix inversion naturally in the system model, it's sort of quite, or yeah, let's say in some sense it's easier to leverage that if your goal is to perform matrix inversion. So I think matrix inversion is definitely an example of a function that is relatively easier to implement. And there might be others, but I think certainly for the linear wave systems that are programmable that I described, matrix inversion immediately comes to mind because you have that matrix inversion in the system model.
But what if you embed your inputs directly into your tunable elements there, right? That's your solution that you're in your, what you call your structural nonlinearity. Is I think that's what you call it.
Yeah.
So can you compute any types of nonlinear function of the input, or actually how does that work? Or is that would really depends on the type of dependencies that you have on your parameters, right?
So, I mean, we do not have a formal proof that would be similar to a universal approximation theorem, but the general idea is that, yeah, if you build some sort of physical neural network architecture where, in this case, we have one input and one output, and we're just trying to basically do a nonlinear regression. And then, in some sense, the question is, well, how expressive can your physical neural network become? So can you approximate highly nonlinear functions? And so there are essentially three mechanisms that contribute to the expressivity, including the encoding nonlinearity. So basically, how do you map your input to the reflection coefficient of the load? Which, for example, if you encode your input into the phase, then you already have a very strong nonlinearity that comes just from encoding your input in the phase. That's actually the most common encoding nonlinearity. Then you have the structural nonlinearity that comes from the mutual coupling. In this setup here, which is a very reverberant small cavity, there's actually very strong mutual coupling between all the elements. So that's also adding a lot of nonlinearity from the multiport network model because this matrix inversion, basically the infinite series, the late terms are very significant. And then the third point is that we can, of course, also stack layers of this transformation. So we don't have to limit ourselves to a single layer. We can do 3, 4, 5 layers. And so combining all of this, it seems that we can reach quite high levels of expressivity.
Yeah. Okay, great. Philipp, thank you so much for your talk. Thank you all for attending, and see you all at our next webinars. I think we're going to have to check the website. I don't remember when it is, but it's coming soon. Okay, thank you all. Have a nice afternoon. Bye-bye.
Many thanks. See you soon.